All right, good morning, everyone. Today we're going to be talking about gases. We're going to be going through all the different gas stuff that we've done. So I am going to go through all the different practice problems that you guys had for your test, which is tomorrow. And if you guys have any other questions, feel free to just ask, okay? So I don't need to only answer these questions. I can just answer whatever questions you guys have. If you want me to slow down on anything, I'll slow down. You just tell me in the chat room. Good morning, Anna. Nice to see you here. And somebody else, whoever else that is, hi. All right. So let's just get started on the review problems, and then we will have some other Q&A time here at the end. So hopefully you guys were able to successfully finish your lab. So the homework is like due right now, but the lab, I think it's due today, but I made it due a little bit later today. So, I'm not too particular about that, but make sure you do turn in the lab some point today. If you guys have any questions about the lab, tell me. And one student didn't have all the ingredients or didn't have baking soda at home, and so she said, hey, can I have extension, which is fine. So if you are missing any ingredient at home, just tell me and you can have an extension for the lab. But make sure you do the lab. Like I said, this is probably one of my favorites through the year, for the year, because it just encompasses so much of the stuff that we've learned, and yet it's a simple reaction itself, right? Vinegar and baking soda. We've done that when we were back in elementary school, but now we're doing it in a sophisticated way and in a very precise way, using all the chemistry we've learned. So I like it a whole lot. Anyway, let's jump into the review. If you guys have any questions about anything, just stop me. Temperature conversions. So super important, and it's a real sad thing when this goes wrong, but for all of your problems, temperature should always be in Kelvin, okay? Make sure you convert it in Kelvin first, or else the answer will definitely be wrong, right? So if we're going from Kelvin to Celsius, well, what do you need to do? From Kelvin to Celsius, we subtract 273. From Celsius to Kelvin, we add 273. So that's simply going to be 817 minus 273. All right. And that's just to the nearest whole number is going to be good enough for our temperatures. Okay, so this is going to be 544 degrees Celsius, right? And then we have a conversion. My bag filled, but it wasn't a lot. So maybe you had your numbers wrong. That's the only thing I can guess. Or, probably you had your numbers wrong. So sorry about that. You can just write out what you did. And if you can figure out what went wrong and, fix your calculations, that's great. But if not, just write out what you did. So, yeah. Sorry. Anyway. This here conversion, we have 17.7 psi. We want to convert it to ATM. Make sure you have the numbers available for you, because this is at home. I might not necessarily, yes, good morning. I might not necessarily give you guys all the different conversions in the test, but it's open notes, so you can always look back at these things. So make sure you come to the test ready with all the conversion factors that you're going to need. Okay, so in this case, when you're converting from PSI to ATM, right, so you're going to say, well, 1 ATM is equal to 14.7 PSI. If we're starting with PSI, make sure you put your PSI down the bottom. Where you're solving for goes in the top. So that's going to be 17.7 divided by 14.7. All right, and that's going to be 1.2. And we have 3 sig figs, so 1.20. All right, so next one, number 3. Why is it easier to cut with a sharp knife than a dull knife? So going back to the very, very first lesson that we had when we talked about pressure and what it really meant. Basically, the easiest way to answer this question is to write out, okay, pressure is what? It's force over area, and pressure is what cuts. So pressure cuts, force pushes. All right? So force isn't what actually cuts something. It's the pressure that cuts something. All right? the greater the pressure, the more easily it's going to cut something. All right, so when we look at the equation of, well, what is pressure? Pressure is force over area. Well, what's different between a sharp knife and a dull knife? A sharp knife is going to come to a point, right? And we have a very small surface area or contact surface area. So it's going to be the knife here at the very tip that's going to touch whatever thing that you're cutting, right? Whereas a dull knife, so this is going to be essentially a sharp knife. A dull knife is going to be something more like this at the end, all right? And this is going to be a large contact area. So when the dull knife touches something and tries to cut it, it's got a much larger value of A. So there's two ways you could essentially understand this, okay? If something requires a certain amount of pressure to cut it, okay, and if you decrease your A, then a smaller force is going to be able to exert the same amount of pressure and cut it. So if you have a smaller contact area, a smaller force is required to cut it. All right, and which is why you only need a smaller force for a sharp knife than a larger force for a dull knife. Or you could explain it a different way. You could say if you exert the same force, then a smaller contact area will create a greater pressure, because decreasing the denominator is going to make this fraction larger, right? So if you have the same force, a smaller contact area means a greater pressure. Okay? All right. Next up, what causes air pressure? Very simple answer that my honor students a lot of them were getting wrong, right? This is very simple, okay? So what causes air pressure is air or gas particles bumping into stuff. And that's it, okay? Gas particles bumping into each other, gas particles bumping into you, gas particles bumping into the sides of the container, all that stuff. Air pressure is simply gas particles or air particles bumping into stuff. When they bump into stuff, right, all those gas particles, when they bump into stuff, that each bump creates a little bit of force, okay? And so you have all those bumping into stuff creates this force that's spread all over the surface area of whatever that particular thing is that you're talking about, okay? So just air particles bumping into stuff. That's it. Enough said. Next one. What is the buoyant force and what causes it? The buoyant force in general is an upward force. Upward force when we're in a fluid. The fluid could be air, or the fluid could be water, or the fluid could be some other liquid or gas or something like that. But what causes it is that the pressure, the pressure below an object is greater than the pressure above. And that's going to be true, oops, just messing up here. That's going to be true for any kind of thing here on Earth, or any kind of liquid or fluid on any planet whatsoever. You're always going to have a buoyant force. Well, why is that? That is because, so if we've talked about this before in terms of, let's say, if you go up a mountain, right? So if you go up a mountain, well, what happens when you go up a mountain? Your ears start to pop. Why do your ears start to pop? Because you have essentially more air below you than above you, right? The air pressure decreases the higher you go up, right? And that's simply because gravity's pulling down on the fluid, gravity's pulling down on the air, makes air more dense close to the surface of the Earth, and it's less dense higher up. So that essentially works for anything, any planet where you have gravity, that the density is going to be greater down lower, and it's going to be less up higher. And that's simply gravity working. Okay, so pressure below an object is greater than the pressure above an object that creates the buoyant force, which is an overall upward force when you're in a fluid. Okay. All right, so next up, we have a man, and this is a true story. You guys look it up. I forget where I saw this. I think it may have been, I definitely saw this on some I don't remember, Mythbusters or something like that. Some video, so you can check it out on YouTube. Some guy can pierce a coconut with only his finger. And the scary thing about this is a coconut is about the same strength as a human skull. So that's really scary. So anyway, a man can pierce a coconut with only his finger if his punch exerts 275 pounds of force, which isn't an extremely large amount of force for an ordinary punch, right? If you're talking about like a boxer, they're going to be punching with over 1,000 pounds of force. And so this guy's force is smaller, but he's punching with only his finger. And so the area of the tip of his finger is around 0.2 or 0.19 square inches. So let's calculate the pressure. And that pressure is going to be the pressure that's sufficient to break a coconut, which is pretty high pressure, right? Pressure is force over area. And so that's going to be 275 pounds over 0.19 square inches. So it's just 275 divided by 0.19, and that's almost 1,500. What do we have? Two significant figures? Yeah, for two significant figures, that's going to be 1,500. 1,500. And what are the units? Think about it for a second. What are the units? We have pounds on the top and square inches on the bottom. So this is pounds per square inches. You can literally write it as pounds per square inches if you want to, but I prefer PSI because this is your pressure unit, pounds per square inches. So either way you can write it like that, or you can write it 1,500 pounds per square inches. Either way is fine. Okay, next one. Now we're getting into our gas laws here, and you need to remember what the gas laws are, and you need to think about, well, why do they happen the way they happen? Okay, so that's important. The why is also important, and we'll get to both of them here in a second. So if the pressure of a gas is doubled and the temperature remains the same, so let's just forget about the temperature, what happens to the volume? And we've done this before. As the pressure goes up, so if we press on something, what happens to the volume? The volume is going to go down. And in fact, if the pressure is doubled, we can say the volume is halved, or the volume is half. And it's important that you write that, okay? You can't just say the volume goes down. You have to say, well, how much does it go down by, right? So the volume is going to be half the original, or the volume is halved, okay? Now, why? And there's two ways to look at this. We could say as you compress, so compressing a fluid is going to decrease the volume. So that's one way. So compressing a fluid, or let's specifically say a gas, will decrease the volume. Or more importantly, what happens when you decrease the volume, okay? So smaller volume means what? It means more frequent collisions. So those gas particles, they're flying around all the time. All those gas particles flying around all the time. If you give them a large space, they're going to bump into stuff a certain amount of time. But if you make the space even smaller, they're going to be bumping into stuff more often. And so when you give it a smaller volume, you have more frequent collisions. So a higher pressure arises because you have a smaller volume. So either way of thinking about those is perfectly a fine explanation. Okay? All right. If you guys have any questions on the front page, please ask. I'm going to go ahead and jump into the second page. Ooh, yeah, let's go this way. And if you want to go back to the front page at any time, just ask. Okay, so if the absolute temperature of a gas is tripled, the volume is held constant, and what happens to the pressure? Okay, so now we need to think about something that's not one of the three different gas laws that we've learned. So this might be a little bit trickier. So really important here. Now the volume is held constant, and we're thinking about the temperature and the pressure. How are the temperature and the pressure related? Okay, and so we can think as we increase the temperature, what's going to happen? First of all, so there's a couple of different parts. The gas particles will move faster. Okay? And so when the gas particles move faster, that's going to create two things. You have more collisions, right? And secondly, the collisions will be more powerful. Why more powerful? Because the particles are moving faster. When you have a faster moving particle, just like a faster moving bullet, it's going to be a more powerful collision than when you have a slower moving particle, okay? So as you increase the temperature, the gas particles move faster, and so you have more collisions, and the collisions are more powerful. So both of these, more collisions and more powerful collisions, means that the pressure is going to increase, okay? So the pressure will increase. But that's not the full answer, right? Because it's telling us specifically if the absolute temperature of a gas is tripled, then what happens to the pressure? It's not just going to increase, but the pressure will triple. Okay? So whatever you do to the temperature, the same thing's going to happen to the pressure. Okay? Just like before for pressure and volume, we said as you increase the pressure, if you double the pressure, the volume is going to be half. As you triple the pressure, the volume is going to be 1/3. So they're going in opposite directions. The temperature and pressure go in the same directions. So as you increase the temperature, the pressure is going to increase. As you triple the temperature, the pressure is going to triple. All right. Next, we have a balloon filled with 208 milliliters of nitrogen at a temperature of 19 degrees Celsius. At what temperature in Celsius would the nitrogen have a volume? So we have, it looks like a Charles Law situation, which means I would first identify what everything is. All right, and let's switch up colors here. So we have this 208 milliliters. That's going to be our V1, our initial volume. And this 308 milliliters, that's going to be our V2, our final volume. Okay? This here, this 19 degrees Celsius, that's going to be our T1. But remember that the temperature must always be in Kelvin. Yes, the question that says, at what temperature in Celsius would the nitrogen have a volume? So we want to get our final answer in Celsius, but we still need to change to Kelvin first. Okay? And so in order to change this to Kelvin, we're going to add 273. So this is going to be 292 Kelvin. So just 19 plus 273 should be 292 Kelvin. So we have our T1 and we want to solve for T2. Why? Because it says at what temperature. So that's our question mark. We're looking for the second temperature, the final temperature. So what we're going to do is we're going to use the equation that we've been given here that you have used all in your homework already, right? So that's going to be your T1 over V1 equals T2 over V2. All right, you're welcome. You guys have already rearranged this in your homework, so you can just go ahead and use your rearranged equations that you have from your homework because it's open notes, right? And so for solving for T2, I'm going to go ahead and rearrange this by multiplying both sides of the equation by V2. So V2 times this and V2 times this, that's going to get me V2 over V2 is going to cancel, and we're left with equation of T2 equals V2 T1 over V1, and that's going to be, our V2 is 308 milliliters, T1 is 292, all over V1 is 208. Milliliters over milliliters cancel, and we're going to be left with Kelvin as our answer there. What's a Kelvin? A Kelvin is a temperature, it's an absolute temperature, and it's based on, so a guy named Lord Kelvin kind of made it up. And so in general, you can say that and it's a little bit confusing because you don't say degrees Kelvin, you just say Kelvin. So Kelvin, your temperature in Kelvin, let's do it this way. Your temperature in Kelvin is going to be your temperature in degrees Celsius plus 273. And it's set that way because 273 or negative 273 degrees Celsius is absolute 0. Which means what? Which means 0 on the Kelvin scale is the lowest possible temperature. So Kelvin, your Kelvin temperature is what's known as an absolute temperature scale. Okay? Absolute temperature scale. So it's your Kelvin is an absolute temperature scale, which basically means you cannot have a negative. You can't be like, okay, it's negative 1 Kelvin. It's impossible. You cannot get lower than 0 Kelvin. All right, back up here. So milliliters over milliliters cancel. Your temperature is going to be in Kelvin. Let's go ahead and do the math. 308 times 292 divided by 208, which gives us 432. 432 Kelvin. Now that's not going to be your final answer, okay? Because it says at what temperature in Celsius. So we need to, I know it's a little bit annoying, you need to go back and convert this to Celsius by now subtracting 273. So we add 273, then we subtract 273 for our final answer, and that's going to be 159. And we're just going to round to the nearest degree. 159 degrees Celsius. Okay? All right. So next up, we have a piston that contains 87.7 milliliters of air in a particular pressure. And hold on for a second. Hold on real quick. I'll be right back. Allison, I'm in class. You're going to have to go up, okay?
But I want to go downstairs. You forgot? You can go downstairs.
All right, sorry guys. Back to number 10. We have a piston, contains this, and a pressure, and a volume, and a pressure. So this looks like a Boyle's Law type problem. So we'll go ahead and identify what's what. This is going to be our V1, right? We know that because it's milliliters. This is going to be our, so PSI, this is going to be our P1, all right? And then the volume is going to decrease. So this is going to be our V2. And what's the new pressure? So we're solving for P2, okay? So let's go ahead and put this into Boyle's Law. Right? And it's important that you guys can recognize milliliters is a volume and PSI is a pressure. All right. So if you didn't know PSI was a pressure, you might be stuck on that. All right. So make sure you identify, okay, PSI, that's going to be a pressure. So P1 V1 equals P2 V2. If we're solving for P2, we're going to divide both sides of the equation by V2. That's going to get us P2 all by itself. So P2 equals P1 V1 over V2. P1 is 22.4 PSI. V1 is 87.7 milliliters. And V2 is 67.4 milliliters. And let's pause before we even solve this. Let's think about, well, what do we expect? If the volume is going to decrease, we would expect the pressure to increase, right? So if the volume increases, we expect the pressure to increase. Or if the volume decreases, the pressure should increase. Let's see if that's actually what happened here. So if it isn't, then we'll need to change something. 22.4 times 87.7 divided by 67.4, and we get out 29.1. And I think we have, yeah, 3 sig figs, so 29.1. Now, what are the units? Well, if we start off with PSI and we start off with milliliters, we have milliliters over milliliters cancel, so that's gone, and our units must be in PSI, okay? All right. PSI means, yes, so PSI is pressure. So PSI stands for pounds per square inch. Pounds per square inch is a pressure units. All right. Now let's go back and think, okay, so we start off at 22.4 PSI and we ended up as 29.1 PSI. So our pressure indeed increases, which is exactly what we expected. So that should be correct. All right, 2 more problems to go. We have a gas cylinder with 3.21 moles of helium. We have a volume and you have a pressure, and you want to know what the temperature is. Now notice in this problem, there's no before and after, okay? There's no change, right? And that lets us know, okay, if there's no before and after, this is going to be like an ideal gas law problem. So it's important that you can distinguish these. So this here, this 3.21 moles, well, that of course is our N, which is moles. The volume, that's our volume. And the pressure, this is a pressure, okay? So we have an N, we have a V, we have a P, and we are solving for the temperature, okay? And once again, it asks us in degrees Celsius. So this is an ideal gas law problem. You don't have a before and after. There's no P1, P2 kind of thing. So we have PV equals nRT, and we're solving for the temperature. So we're going to divide both sides by nR. That's going to cross out this, and it gets us temperature is PV over nR, which is going to be a pressure of 12.5 atm. Now remember, for the previous problems, it doesn't really matter what units your particular thing is in, whether it's, you know, gallons or psi or whatever. But for the ideal gas law, it's important because R is a specific number for particular units. So the pressure must be in atm, okay? The volume must be in liters. Well, thankfully it is, so we don't need to convert anything. So volume is at 7.15 liters. So pressure must be in atm, volume must be in liters, your N must be in moles, which it always is anyway, 3.21 moles, because R is 0.08206 liters atmospheres per mole Kelvin, okay? So the units of R tell you the units that everything else must be in. So let's do the math. That's going to be 12.5 times 7.15 divided by 3.21. And you can either put the denominator in parentheses or simply just divide twice. Divide by 3.21, divide by 0.08206. And that's our answer, 339. And the units of this are K, Kelvin, because the units of R are for Kelvin. And any of these things are going to give you the temperature in Kelvin. But it says, what's the temperature in degrees Celsius? So we have one last step, and that is subtract 273 to convert it back into Celsius. So that's going to be 66. So 66 degrees Celsius. All right, any questions so far? Okay, one last problem. A nice, difficult stoichiometry problem, just like or similar to what you guys did in your lab. All right, actually this one's maybe even a little bit harder, but it's, you know, it's a test question rather than a lab one. So we have balance of final this reaction, okay? So we have this reaction, this is nitrogen triiodide, which is an extremely explosive solid. It's kind of interesting to work with. I've used it before, made it before, kind of crazy stuff. All right, nitrogen triiodide, and when it decomposes, when it explodes, it turns into nitrogen and iodine. All right, and so we have, I'm going to go ahead and start with the iodine because we have 2 here and 3 there. And you can start with the nitrogen if you want. But if you have a 3 here and a 2 here, you're going to need to make this 2 and make this 3. So that's going to be 6 iodines and 6 iodines. So now we have 2 nitrogens and 2 nitrogens. And so that went ahead and also balanced the nitrogen at the same time. So we're all balanced. Make sure you balance these before you actually solve them. Now, we have 10 grams of nitrogen triiodide that explodes, and we want to calculate the total volume. If these things were to expand to their maximum potential, what would the total volume be? Now, 10 grams is not a very large amount. That's probably about the size of like an eraser, an ordinary eraser, 10 grams. It's not a whole lot, all right? It's about an eraser. Maybe, maybe even a little smaller, but, depends on the density of these things. So 10 grams. What should the volume of that turn into? We're turning into 2 gases. So when I said this is a little trickier than the one in the lab, simply because rather than making 1 gas, we're making 2 different gases, okay? All right, let's go ahead and do this. Let's see, we have 10 grams of Ni3, and we want to know how, let's do it this way. We want to know how many moles of gas we produce. All right, so the first thing that we need to do is we need to convert this 10 grams into moles. So we need the molar mass of nitrogen triiodide to do that. Now it is going to be a pretty heavy thing because iodine's pretty heavy itself. So nitrogen and 3 iodines. It's going to be 1 nitrogen, that's 14.007, plus 3 iodines, so that's 3 times 126.9. Well, that's going to be big because we got 3 iodines. 394.7, that's huge, right? So 1 mole has a mass of 394.7 grams. And so the first thing we're going to do is we're going to take that 10 grams and convert it into moles. But now the next step is we want to convert from moles of nitrogen triiodide to moles of gas. All right, so this is going to be 2 Ni3. Where'd this 2 come from? Came from the balance reaction. And then we're going to have moles of gas up here. Now, like I said, there's more than one way you could really think about this. But you have 1 mole of N2 and 3 moles of I2. So this is going to be really a 4 on the top, right? This is going to be, let's scratch this out. This is going to be 1 N2 plus 3 I2, which is going to be 4. So the top here is going to be 4. Okay? So 4 gas products. All right? And if there was only 1 gas product, then you would just worry about that 1. But because there's 2, we have to add the 1 of the nitrogen plus the 3 of the iodines. So this is going to be, let's do the total math. We start off with 10. We're going to divide by that molar mass of the nitrogen triiodide. So that's going to give us this number. So that's our moles of nitrogen triiodide. And then we're going to multiply it by 4 over 2, which is the same as multiplying it by 2. Okay? So times 4 over 2, or you can just simply say times 2, and that's the same. That's going to get us 0.05 moles of gas. 0.05, and let's just keep some numbers here, 0.67 moles of gas. The last step now, so this is kind of the opposite of what you guys did in your lab before. You use your ideal gas law to figure out moles and then your moles to figure out grams. Now, in this case, what we're doing is we're doing the opposite. We're going from grams to moles of gas, and now moles of gas to the ideal gas law. And so we have PV equals nRT, solving for now the volume, right? Calculate the total volume. So for solving for volume, we're going to divide both sides by P, and that gets us your volume is nRT over P. P over P over cancel. And let's go ahead and plug in some numbers. The N, very importantly, the N here is moles of gas. Okay? So that's our 0.05067 moles. And once you get that, everything else is going to be falling into place. 0.08206 for R. Your temperature, we said, assume 1 atmosphere and a temperature of 30 degrees Celsius. I suppose just like a little bit warmer than room temperature because this is going to be hot. And so 30 degrees Celsius, so that's going to be 273 plus 30, so it's going to be 303 Kelvin over a pressure of just 1. All right, So last of all, let's take our moles, which is at 0.05067, times R, 0.08206, times 303, and that gets us 1.26. I'll divide by 1, but we don't need to put that in there. So 1.26. What are the units? What are the units? The units are going to be found on the units for R. R has the units of liters, atmospheres per mole Kelvin. So mole over mole cancel, Kelvin over Kelvin cancel, ATM over ATM cancel, and we're left with liters. So 1.26 liters. Okay? All right, guys. Any questions? That is it for the review, but I want to see if you guys have any questions on anything. There's only 5 of you. There's like 5 people online. Everybody else is like sleeping. They're going to check this out later. They're going to, wait till the last minute to prepare for the test. Don't wait too long, all right? So you guys have limited time to do the test. So make sure you spend a little bit of time preparing for the test. I'm talking to all you guys that are on here now are going to be prepared, but the 15 other people, I don't know. So how do we balance? All right, I can answer that here in a minute. Anybody else from my class? Do you guys have any questions before we have a test tomorrow? Should we expect the test to be similar to this? Yes, you should expect the test to be similar to this. And let me say, we've had, I think, so this one is a little bit tricky. I think your problem like number 12 will actually probably be more similar to the one that you guys did in the lab. Okay, so more similar to that than it will be to this. But otherwise, expect something very, very similar to the review. Okay, obviously the chemicals are going to be different, the numbers are going to be different, but the equations are going to be all the same kind of stuff. I'm not going to have as many. So you guys had like, so I'm not, I don't know, these explain questions might be a little different. Don't expect them to be word for word the same. They might be a little bit different. And so just be prepared for that. Okay. Be prepared with all the stuff you guys have done in your homework. Yeah. Any other questions? Anna, you good? All right. So if there are no further questions from my class, somebody did have a question on balancing, and I can go over balancing real quickly here. Okay. But I can't stay for too long because I do have some other classes I need to get to in a second. So for balancing basically what we're trying to do is you're trying to get the same number of the different chemicals or the different elements all on, equal on both sides. So if you have something like, let's say, H2 plus N2 makes NH3, well, you notice that you have 2 hydrogens, here you have 2 nitrogens, here you have 1 nitrogen, 3 hydrogens. So this is not balanced, right? What do I mean by not balanced? I mean that there are not the same number of elements on both sides. Well, why is this important? This is important because in real life, you don't actually destroy or create atoms in a chemical reaction, right? In a chemical reaction, all that happens is the atoms change how and with what they're bonded. Okay? So your atoms change their bonding. So the atoms that you start off with must be exactly the same number and same type of atoms that you end up with. That's the heart of what balancing is all about. You need to have the same number and the same type of atoms on both sides of the chemical equation. Okay? And so the way we do that is we simply look at these numbers down here. Okay? And you can start with, so this is a kind of a simple one. It doesn't matter whether you start with hydrogen or start with nitrogen, but we're going to start with one element at a time. So you always do, or balance one element at a time. And it doesn't matter a whole lot which one you start with, but you try to start with the easier one. And the easier one is going to be the one that's in the least number of chemicals. Now, in this case, we don't have specifically an easier one, okay? So what I'm going to do is I'm going to start with nitrogen because I have 2 nitrogens here and I have 1 nitrogen here, right? And so I need to get them the same number on both sides. So I'm going to go ahead and put a 2 right there. So I have 2 nitrogens and now I have 2 nitrogens, same number of nitrogens on both sides. That's balanced. Next, I notice I have 2 hydrogens here, but I have 6 here, right? 2 times 3 is 6. So I have 6 hydrogens on this side. So I need to make sure I have the same number of hydrogens on this side. And the only way I can do it is by putting a 3 in front there. What's that 3 do? 3 times 2 is 6, just like 2 times 3 is 6. So that balances the hydrogen there and there, okay? So this reaction is now balanced. We have the same number of hydrogens and nitrogens on both sides. All right, I'll do one more challenging one here real quick, okay? So we can do something like, let's say, C2H6 plus O2 makes CO2 plus H2O. This is a bit more challenging. When you balance this, the thing that you have to do is you always start with the easier one, which essentially means that you're going to not balance oxygen first. Why? We're going to balance oxygen last because oxygen is in 1, 2, 3 different things. Okay? Notice carbon is in 1, 2 things, right? Carbon's in 2 things. Hydrogen is in 2 things, but oxygen is in 1, 2, 3 things. So we're going to balance oxygen last because it's the hardest one to do. Okay? So the first thing I'm going to do is I'm going to start with carbon. You can start with hydrogen. It doesn't really matter. So if I have 2 carbons here, right, and I have 1 carbon here, I'm going to put a 2 in front there. Okay? Now I have 6 hydrogens here, and I have only 2 here. So in order to get 6 on this side, I need to say, okay, what times 2 equals 6? 3 times 2 equals 6. And so that's how I balance the hydrogens. So 3 times 2 is 6, and 6. So hydrogen is now balanced. Carbon is now balanced. The only thing that's left is oxygen. Now, oxygen is a little trickier because we have oxygen in 3 different things. So what I need to do is I need to add up all the oxygens I have on the right side. So I have on here, I have 2 times 2 is 4, plus 3 times 1 is 3. So this is 4. There's 4 oxygens here, and there's 3 oxygens here, which means I have 7 oxygens on the right side, a total of 7 oxygens on the right side. Okay? So in order to balance it over here, we have O2. And so we say, okay, well, what times 2 is 7? Well, there's no whole number times 2 is 7, right? So the only thing times 2 is 7 is 3.5. 3.5 or 3.5 times 2 is 7. Now that's going to balance it. But we have a problem. You can't have a 3.5 here. You can't have a decimal here. So how do we get rid of the decimal? There's one way that we can get rid of the decimal rather than start over. And that's this. We can multiply the whole thing by 2. All right, let's multiply the whole thing by 2. So that means we're going to have what? We're going to have now 2 C2H6 plus 3.5 times 2 is 7 O2 is going to make 2 times 2 is 4 CO2, and 3 times 2 is 6 H2O. And that is our balanced equation for this problem here. Okay? A little tricky on this last one, and I'm going to go ahead and leave it there. If anybody has any last minute questions, go ahead and shoot me now, but I'm going to go ahead and sign out. See you guys.